We will now use the concepts we developed in the first part of this lesson to solve problems. To begin with, let's recall some of the formulae we developed. Now, can you recall some of those formulae? Well, the first formula is the wave equation. Wave speed equal to frequency multiplied by the wavelength. I hope you remember the definition of wavelength. Can you give me one definition of wavelength? I give you three. Wavelength is the distance advanced by the wave in a time of one period. It is the distance between two nearest particles that are in the same phase of vibration. And for a transverse wave, it's the distance between two nearest or adjacent crests or two adjacent troughs. For a longitudinal wave, it will be the distance between two adjacent high pressure regions or two adjacent low pressure regions. Okay, what is the second formula that we looked at? The speed of transverse waves on a stretched string, V equal to square root of T over mu. T is the tension on the string, mu is the mass per unit length. Alright? The third formula we developed was for the energy. The energy transmitted along a string of length delta x is 1/2 mu a squared omega squared delta x. Mu is the mass per unit length. Tell me, how do you find the mass per unit length? If you know the mass of the string and you know its length, total mass divided by the length will be mass per unit length. If you know the mass per unit length and the length of the string, you see, mu times delta x is the mass of the string. A is the amplitude of vibration. What is the amplitude? Amplitude is the maximum displacement, and omega is the angular frequency, which is related to the frequency of vibration as omega equal to 2 pi f, or omega is 2 pi divided by the period. Alright, all these you must be familiar with. And finally, the power transmitted along a stretched string is 1/2 mu a squared omega squared v, where v is the speed of wave on the string. Alright, let's use these now to solve a few problems. Example 1. One end of a string 6 meter long. The length of the string delta x equal to 6 meter is moved up and down with simple harmonic motion at a frequency of 60 Hz. The wave reaches the other end of the string in 0.5 seconds. What is the wavelength of the wave in the string? We want to find the wavelength. Now, what is the equation which is relevant in here? If you want to find the wavelength, you need the frequency of the wave that is given to us. We also need the wave speed, because the wave equation connects the wave speed, wave frequency, and the wavelength. So, if you want to find the wavelength, I need the frequency and the wave speed. I've got the frequency. Is there any way I can find the wave speed from the given information? Yes. A length 6 meter, the energy of the pulse travels a distance of 6 meter in 0.5 seconds. Distance traveled is given, the time is given, we can calculate the speed. Alright, always start a problem with the given data. Delta x equal to 6 meter, the frequency f equal to 60 hertz, delta t, the time taken by the pulse to reach the other end of the string, is 0.5 seconds. The wave travels the length of the string in 0.5 seconds. Therefore, wave speed v equal to delta x divided by delta t. That is 6 meter divided by 0.5 seconds. That is 12 meter per second is the speed of the wave. Now we have the speed, we have the frequency, we can now find the wavelength. We know v equal to f lambda. Therefore, lambda, the wavelength, is v divided by f. Now, v is 12 meter per second. Frequency is 60 hertz. Therefore, lambda is 0.2 meter. Okay? Another one. Example 2. The wavelength of violet light is 7 times 10 to the negative 7 meter. If the speed of light is 3 times 10 to the 8 meter per second, what is the frequency of violet light? I hope you know by now that the colors that you have in white light, the colors are different because of the frequency and the wavelength. Each color corresponds to a particular wavelength and therefore a particular frequency. Now, what is common to all colors is the speed. All colors travel with the same speed in vacuum, and that speed is 3 times 10 to the power of 8. Speed of light is a constant, and its value is 3 times 10 to the 8 meter per second. Now, the wavelength of violet light is given. The speed we know, therefore we can find the frequency. All we need to do is use the wave equation. So, lambda is 7 times 10 to the negative 7 meter. Speed of the wave is 3 times 10 to the 8 meter per second. And we use the equation v equal to f lambda. I told you this wave equation is equally applicable to mechanical waves and electromagnetic waves. Light is the form of electromagnetic waves. We have v equal to f lambda. We need to find the frequency. Solve for the frequency. F equal to v over lambda. That will be 3 times 10 to the 8 meter per second divided by 7 times 10 to the negative 7 meter, and that is 4.29 times 10 to the 14 hertz is the frequency of violet light. Okay, let's do another one. A steel wire is 7 meter long and has a mass of 100 grams. Now watch the information given here in the first sentence. I have given you the length of the wire. I have given you the mass of the wire. Can you use those two quantities to calculate the mass per unit length? Yes, you can. Alright, it is under a tension of 900 Newton. It is stretched by using a force of 900 Newton. What is the speed of transverse pulse on this wire? So here we are talking about a stretched wire. We need to calculate the speed of transverse waves on that string. Can you recall the equation we developed for the speed of transverse waves on a stretched string? Alright? It is V equal to square root of the tension T divided by mu, the mass per unit length. Now what do we have? We have delta X equal to 7 meter. Mass of the string is 0.1 kilogram. Is that right? 100 gram is 0.1 kilogram. And the tension of the string is 900 Newton. Well, If you have delta x, the length, and m, the mass, we can find the mass per unit length. So first we obtain the mass per unit length as mu equal to mass divided by the length. Is that right? Mass per unit length. That will be 0.1 kilogram divided by 7 meter. And what's that equal to? That will be 0.0143 kilogram per meter. That is mu, the mass per unit length. We now have the tension. We have the mass per unit length. Therefore, speed of transverse wave on the string V equal to square root of T over mu. Let's use those values. T is 900 Newton. Mu is 0.0143 kilogram per meter. And calculate that. Now always remember, when you listen to the lectures, especially the problem solving sessions, keep your calculator, piece of paper with you so that you can work along with me. Use your calculator and work it out. And make sure that the answers I have given you are the right ones. Sometimes I make mistakes. Alright, I got it as 251 meter per second as the speed of transverse wave on that string. Okay, let's do another one. Transverse waves travel at 150 meter per second on a wire of length 80 centimeter, that is under a tension of 500 Newton. What is the mass of the wire? So this time we need to find the mass of the wire. Well, look at the data. What do we have? We know the speed, we know the tension. You see, there are three quantities involved there: speed, tension, and mass per unit length. If you know the speed and the tension, we can use those two values to find the mass per unit length. Is that right? And once you know the mass per unit length and the length of the wire, we can calculate the mass of the wire. That is the strategy for the problem. Alright, let's pick our data. The length of the string is 80 centimeter, that is 0.8 meter. The speed of transverse waves in that stretched string is 150 meter per second. The tension is 500 Newton. First we obtain the mass per unit length mu using the equation for wave speed. What is the equation for the speed of transverse waves in a string? It is V equal to square root of T over mu. Can you mentally solve for mu from here? Alright? You can see V squared, if you square both sides. V squared equal to T over mu. Therefore, mu will be T divided by V squared. Is that right? So, V squared equal to T divided by mu. Therefore, mu equal to T divided by V squared. Let's use those values. V is 150, T is 500. That will be 500 Newton divided by 150 meter per second squared. And that is 0.0222 kilogram per meter is the mass per unit length. Alright? If you know the mass per unit length, and if you know the length of the string, how will you find its mass? The total mass will be the mass per unit length multiplied by the length. So m equal to the length multiplied by mass per unit length. That would be 0.8 meter multiplied by 0.0222. Make that correction there. You see how I make mistakes? And that should be, I want you to check this result. I'm going to leave it there like this, and I want you to check it. I think I made a mistake because I dropped that 0. So check that and correct this on your own. Okay? Let's go and do another one. A wave pulse propagates along a wire in the positive x direction at 20 meters per second. What will the pulse velocity be? A. If we double the length of the wire, keeping the tension and the mass per unit length a constant. Well, so we keep the tension and the mass per unit length a constant. We double the length of the string. What will happen to the speed or the velocity of the wave on that string? Can you tell me now? Just look at my face and tell me what's the answer. We keep the tension and the mass per unit length a constant. Well, I hope you gave me the answer. The speed of transverse wave on a stretched string depends only on tension and mass per unit length. Is that right? V equal to square root of T over mu. If you keep those two quantities a constant, that means the speed will remain a constant. The speed does not depend on the length. I hope you understand my argument. Alright, V equal to square root of T over mu. The velocity of transverse wave on a wire does not depend on its length. Therefore, if you made the length twice or 3 times or 100 times, it will not affect the speed of waves on that wire, because the speed depends only on the tension and the mass per unit length. Okay, now what's the B part? Double the tension. You double the tension while holding the length and mass per unit length a constant. You keep the value of mu a constant and double the tension. What will be the speed now? Alright, we start by using the same equation. V equal to square root of T over mu. When the tension is doubled, let the new velocity be called V1. Then what will V1 be equal to? V1 then equal to square root of 2T divided by mu, because the tension is doubled. Alright, we can now write this as, isn't it, if you know a little algebra, the numerator can be written as square root 2 times square root T. Or simply square root 2 can be separated. It becomes square root 2 times square root of T over mu. And what is this equal to? Square root T over mu is the original value of the speed, which is 20 meters per second. So that will be square root 2 times the original speed, and that will be square root 2 times 20, and that will be 28.3 meters per second. That means you increase the tension, the speed of propagation on that wire will increase. Is that right? Now, you want to tune a guitar wire. You are actually increasing or decreasing the tension. You see that? We will talk about that sometime later again. Now, the third part, you double the mass per unit length while holding the other variables a constant. So this time you double the mass per unit length, double mu, keeping T a constant. What will happen to the speed? Can you tell me what the answer will be? Just tell me, will the speed increase or decrease? You double the mass per unit length, make the wire thicker. Will the speed increase or decrease? Well, let's find out. Alright, when mu is doubled, let the new speed on that wire be called V2. Then what is V2 equal to? V2 is square root of T over 2 mu. Mu is doubled. Now, the same way we did in the previous example, this square root 2 can be separated, but that is going to be on the denominator this time. This belongs to the denominator. So look at the way I wrote it. 1 over square root 2 times square root T over mu. I hope you understand that one. Now, what is this quantity now? Square root T over mu is the original speed, which is 20 meters per second. So how can you write this one now? This is V. V multiplied by 1 over square root of 2. 1 over square root 2 multiplied by V. And that will be, that V of course belongs to the numerator. That will be 20 meters per second divided by square root 2, that is 14.14 meter per second. That means when you increase the thickness of the string, the speed of waves on that wire decreases. So on a thin wire, the speed will be greater than on a thick wire. Okay, let's move on. Example 6. The cable of a ski lift runs 400 meters up a mountain and has a mass of 80 kilograms. When the cable is struck with a transverse blow at one end, the stretched cable is given a transverse blow. What is the meaning of a transverse blow? If this is a string, a transverse blow is the blow at right angles, creating a pulse. Just like I created the pulse on the spring. So the pulse will go all the way to the other end and get reflected back. Now what happens here? When the cable is struck with a transverse blow at one end, the return pulse is detected 12 seconds later. The energy advanced all the way to the end of the cable and it got reflected, and the energy came back in how long a time? 12 seconds. The time taken for the energy to travel along the length of the wire one way and back is 12 seconds. What is the speed of the wave? What is the tension in the cable? Well, speed can be found very easily. How? We know the distance traveled by the pulse. What is the distance traveled by the pulse? The pulse travels from one end of the cable to the other and back. The length of the cable is 400 meters. So one way it travels 400 meters and back it travels 400 meters. What is the total distance traveled by the wave pulse? It is 800 meters. And what is the time taken for that? It's 12 seconds. You can find the speed of the wave right away. The length of the cable is 400 meters. Its mass is 80 kilograms. The time taken by the pulse to go all the way up and back is 12 seconds. 12 seconds is the time for the pulse to travel the length of the cable and return. And therefore, the speed of the wave along that string is twice the length of the wire. I hope you understand why twice the length of the wire. It has to travel one way and back, divided by delta t. That will be 2 times 400 meters divided by 12 seconds. That is 66.7 meters per second. That is the speed of the wave. Now, we need to now find the tension in the cable. Now, how is that going to be? We know the speed, we know the mass of the cable, we know its length. If you know the mass and the length, what quantity can you obtain from there? You can obtain the mass per unit length. So you can find mu from these two values. We know the speed, therefore we can find the tension. Is that right? Okay, let's do that. Now, mu equal to the mass divided by length. Mu is mass per unit length. That is 80 kilogram is the mass, length is 400 meter. Therefore, the mass per unit length is 0.2 kilogram per meter. And now we have V equal to square root of T over mu. We know the value of V, we just calculated it. V is 66.7 meter per second. We know mu, we just calculated it. Therefore, you can find T. Again, square both sides. V squared equal to T over mu. Therefore, T equal to V squared times mu. And that will be 66.7 squared times 0.2. That will be 890 Newton. You can see most of the problems we solve in here are straightforward problems like this. So please take some time and solve more problems like this. Do your homework. Make sure that you do all the homework problems that I have supplied. Let's look at another problem. A harmonic wave on a string with a mass per unit length of 0.05 kilogram per meter and a tension of 80 Newton has an amplitude of 5 centimeter. Each section of the string moves with simple harmonic motion at a frequency of 10 Hertz. Each section of the string moves up and down with a frequency of 10 Hertz. Find the power propagated along the string. Now, is there anybody who remembers that equation for the power propagated along a stretched string that we developed? Power, 1/2 mu omega squared A squared V. Is that right? Well, I hope so. Okay, let's pick our data. We got the mass per unit length is 0.05 kilogram per meter. The tension is 80 Newton. Amplitude of vibration is 0.05 meter. And the frequency of each segment is 10 Hertz. Well, if you now look at these, can we obtain everything that we need? The power transmitted is 1/2 mu is there. Omega squared, omega can be obtained from the frequency. Now, what is the relation between omega and the frequency f? Omega equal to 2 pi f. Alright, omega squared, A squared, you know A, times V, the speed. We now need to find the speed. Now, how do we find the speed of transverse wave on the string? If you know the tension and you know the mass per unit length, you can calculate the speed. Now look at that, we can find all those quantities. The power propagated along a stretched string is given by P equal to 1/2 mu A squared omega squared V. And of course we have mu, we have A, we have omega, how? Omega equal to 2 pi f. And we have V, how? Because we know T and mu. So first let's obtain V. V equal to square root of T over mu. That will be square root of 80 Newton divided by 0.05 kilogram per meter. Alright, calculate that on your own and see whether you get my value. I got it as 40 meter per second. Alright, please check it. Okay, omega equal to 2 pi f, f equal to 10 hertz, that would be 2 pi multiplied by 10 hertz, that is 20 pi hertz. You can leave it in terms of pi. Alright, now let's bring all these quantities together. You know mu, we know A, we have now obtained the value of omega, we know the value of V, put it all together, and that will be P equal to 1/2 mu A squared omega squared V, replaced with their values, and I got it as 9.87 watt is the power transmitted along the length of that string. Now remember, wave motion is a mode of energy transfer. So how much energy is transmitted along the wave is an important concept. What is the rate at which this energy is transmitted? The rate at which the energy is transmitted is what we call power transmitted. Alright, let's try another one. Waves of frequency 200 Hertz and amplitude 1.2 centimeter move along a 20 centimeter string that has a mass of 0.6 kilogram and a tension of 50 Newton. What is the average total energy of the waves on the string? What is the average energy transmitted along the string? What's the equation for energy transmitted? Well, 1/2 mu omega squared A squared delta x, which can be replaced by V times T. And then finally, what is the power transmitted past a given point on the string? Alright, the first thing we need to do is to pick our data. What are the given data we have? M, the mass is 0.06 kilogram. The tension is 50 Newton. Amplitude of vibration is 0.012 meter. The frequency is 200 Hertz. And delta x, the length of the string, is 20 meter. So you can see what good does this do, picking up all the data. Okay, now delta E, the energy transmitted, is 1/2 mu A squared omega squared delta x. Alright, what do we have? Mu, you have the length, you have the mass of the string, you have the length of the string. Can you calculate mu? Mu is mass divided by the length. The amplitude is given to us. Omega can be calculated from the frequency value, and delta x is given to us. So let's get these values. Mu equal to m over delta x, mass per unit length. That will be 0.06 kilogram times 20 meter. That is 0.003 kilogram per meter. And that is our mu. So we got the value of mu. Omega equal to 2 pi f. F is 200 Hertz. That will be 2 pi times 200 Hertz. That will be 400 pi Hertz. I think we have now all those values. Therefore, delta E is 1/2 mu, we pick that value, times A squared, amplitude squared, times omega squared. Omega is 400 pi, square it. Look at the way I have squared it. The quantity 400 pi. So when you put that in the calculator, take care. Put that 400 pi inside the parenthesis and square it. multiplied by 20. And I got it as 6.82 joules as the average energy transmitted along the length of the string. Alright, what do we now need? We need to find the power transmitted past a given point, the rate at which the energy is transmitted. Now, how will you get that? Well, the power, if you can look at this, the power will be 1/2 mu a squared omega squared v. So we need the value of v, the speed. Alright, let's do that in the next slide. V equal to square root of t over mu, and that will be square root of 50 Newton divided by mu is 0.003 kilogram per meter, and that will be 129.1 meter per second. I have V, I have omega, I have A, I have mu. All those values that I need are present here. Let's use it to find the power. Power is 1/2 mu a squared omega squared v, and that will be, put all those values. Mu is 0.003, amplitude is 0.012 meter, omega is 400 pi times v, the speed is 129.1 meter per second. And what does that give you? It will be 44 watt. Okay, I think we did a number of problems, and these are representative problems that you must be familiar with. Alright, I'm going to stop this lesson here, and in the next lesson we're going to develop further on the study of waves. If you remember, I used a term in this problem, harmonic wave. What is a harmonic wave? A harmonic wave is a wave generated due to the simple harmonic vibrations of the particles. Alright, so we are going to use the equation of a simple harmonic vibration to study harmonic waves in our next lesson. Alright, I'll see you for the next lesson a little later.